Okay, this is Jack Jackson. We got another video here on complex number operations. This one we're going to be talking about powers and roots of complex numbers. So let's just look at an example to start with. If we let z be a plus bi, or in other words r e to the I theta, then we have z cubed is r e to the I theta cubed, which literally means r e to the I theta times r e to the I theta times r e to the I theta. In other words, z times z times z. So 3 z's multiplied together. Well, because of what we know about what multiplication means, this means we're going to multiply these. When we multiply two of these, we multiply the r's. So we're going to multiply all 3 r's ultimately. And we're going to add the thetas. So we're going to add 3 thetas all together. So when we're multiplying the 3 r's together, that becomes r cubed. When we multiply these parts here, we're adding the exponents, and we add the 3 thetas. Well, adding 3 thetas is multiplying that by 3. So basically we get what you would think would work just like real numbers for properties of exponents, which is why we use this convenient notation. So this gives us r to the third power is our absolute value, and we end up multiplying the angle by 3 there. So we're multiplying the power by 3, which is the angle. Well, it's the angle times I. So this is a natural way then to define powers for any number n for the exponent. Is we have z to the n, we just take r e to the I theta to the n. That's just r to the n, and e to the I theta is just multiplying that by n. And so this would certainly be nice for a positive. So if n is a positive number, for example, then we get r to the n is going to be the magnitude then of the power of the number raised to the power, and then the angle is just going to be multiplied by n. So for example, if we square it, we're going to square its distance from the origin, but we're going to double its angle. Or if we cube it, we're going to raise the distance from the origin, its absolute value, by the power 3, but we're going to triple the angle. Now, this has some interesting things to say when we get to roots. So remember that radicals or roots are just fractional exponents in disguise, but particularly radicals. So a square root of z, for example, means z to the 1/2 power, or the nth root of z is z to the 1 over n. So if we have z to the 1 over n, that's the same thing as saying the nth root of z. And of course, remember, we've seen this before too. One way we could write this, z to the m, and then the nth root is z to the m over n power. So we can use these kind of rules that we know, rules of exponents, still work. Okay? So if we're taking an nth degree radical, that is, we're raising to the 1 over n power, what's the end result? Well, the end result is you're going to take the nth root, or raise to the nth power, or 1 over nth power, nth degree radical of its absolute value, its distance from the origin, but the angle is going to be divided by n. Okay? Now, if you have an equation that looks like z to the n equals some constant, so we're thinking of r e to the I theta as some constant, and z is our variable. So, for example, we might have an equation, well, let's just do a real simple one, z cubed equals 1. They're actually, the solutions to this are the cube roots of 1, and there's actually 3 of them. In fact, we could use some algebra to solve for them. Z cubed minus 1 equals 0. This factors as a difference of 2 cubes, so that's z minus 1. Square the first term, square the last, multiply and change the sign for the middle. And you could work this out. Let's work this out and just verify that that is correct. Multiply everything by -1. Multiply everything by z, and line up like terms, and we get z cubed. Those disappear, minus 1. Well, then this means z minus 1 equals 0, which says z equals 1, or z squared plus z plus 1 equals 0. And you probably remember the quadratic formula here, that this says z equals, let's see, the opposite of b over 2 times a. I like to write it like this, in two fractions, plus or minus the square root of b squared. Remember, you have a z squared plus bz plus c equals 0. Z equals minus b over 2a plus or minus square root b squared minus 4ac over 2a. And if the b squared minus 4ac is a negative, this part will be something times I. So it's already split into real and imaginary parts. So this is 2 times 1. Top is b. Everything's all a, b, and c are all 1. So this is negative 1/2 plus or minus, and this is negative square root of negative 3. And so we get, altogether we get 3 answers. Z is 1, or Z is negative 1/2 plus the square root of 3 over 2i, or it is negative 1/2 minus the square root of 3 over 2i. So those are our 3 answers in rectangular form. So all 3 of those are called the 3 complex roots of z cubed, of 3 complex roots of 1, I should say. The solutions to z cubed equals 1. So in general, when you have z to the n equals some constant, there'll be n solutions in the complex number system. Okay, and they're called the cube roots of this, or the nth roots of that constant. Okay, one of these can be found in polar form very nicely. So let's go back to here, and one of them, if your constant can be written in polar form as r e to the I theta, then one of them is just the nth, the 1 over nth power of this. So z to the n to the 1 over n would cancel and give you z. Here you get r to the 1 over n, and e to the I theta divided by n. So that would be one of those examples. So let's take a look. Let's actually work that one out here. So this is r is 1 and theta is 0. And so right here is the number 1 in blue, that point there. And then we can look at its cube roots. Well, one of them is the same number, it's 1, and here are the other 2 right here. Okay, so it turns out, so this one right here in the second quadrant is this one, negative 1/2 plus the square root of 3 over 2i. And this one right here is in the third quadrant, and that is this one right here. And of course this one's just 1. Notice that they're evenly spaced around a circle. They're all a distance of 1 from the origin. So if you take the whatever size, the r value here, you take it to the 1 over n power, that'll tell you how far out all these are, and then they're all evenly spaced. So pretty cool, huh? So let's look at some other examples. So what if we let's take something bigger like r is 8, and it's just 8 only. Then the actual point is way out here. There's our point V, and its cube roots are these 3 points here. One is just 2, and then you have these other 2 here. Okay, or what if I put negative 8? Negative 8 is my V value, and then we can look at its cube roots, one of which is negative 2, and here are the other 2 out here, also a distance 2 from the origin, but they're evenly spaced. So we have 3 roots, so we take 2 pi divided by 3, and that's the angle between any 2 of these roots and from the origin. So you go from this point, well, from this point here to the origin to this one, and that's 2 pi over 3, and then 2 pi over 3 to this one, 2 pi over 3 back to here. Okay, so all of the roots then are r to the 1 over n, e to the I, and one of them is theta over the original theta over n, and the others then you add to that value 2k pi over n, and you let k go 1, 2, up to actually it should start at 0 up to n minus 1. Okay. Well, what if we have something that's not a whole number? Well, let's take something here and look at fourth roots. Aha, I've got to change something here. This should be the absolute value. Because this guy should be, oh, we should not have a negative number for an r. There we go. Okay. But if we wanted it to be negative 8, we would put an angle here. So I should have put, we should put an angle of pi there. That's the number. R is 8. Pi is theta. That's the number negative 8, the real number negative 8. So you should always make r be a positive number. So these are the fourth roots of 8, the fifth roots of 8, sixth roots of negative 8, and so forth. And notice how much bigger, the bigger you let n be, the more roots you have. You have exactly n roots. So there are n of these red points. Of course, if you go back to 1, we get to the point there. Also notice that as we take this bigger root, so here are the two square roots of negative 8. One is here, which is a pure imaginary number. Notice the real part's 0, and this is something here. Well, it's, what is it? It's 2 square root of 2, right? That's 2 square root of 2 is the radius. Okay, and it's that times I, and negative 2 square root of 2 times I if we do it in rectangular form, or if we do it in polar form. Here we have it. So the angles are, well, pi over 2 and minus pi over 2. For example, if we did the cube roots, there they are. Okay, and we can do this at other angles. Let's see. Let's make this pi over 4, for example. Now notice they just kind of rotated. So one of the roots is this one right here. That's the first one, which one I'm calling Z1, and that's going to be the first. That's going to be the one where the angle is pi over 4 divided by 5. So that angle is pi over 20. Okay, and but the radius is the fifth root of 8. And all of these, the radius is the fifth root of 8, and they're just shifted. So if this is pi over 20, this is pi over 20 plus 2 pi divided by 5. Anyway, and so they just kind of shift around like that. Here are the sixth roots of 8, and so forth. And so you can, well, not of 8, excuse me, of 8 times e to the I times pi over 4. Okay. Let me make this smaller. Okay, now you can see this point. There's the original point, V. So I'll tell you what, let me make this blue, because that is the point V right there. And if we solve the equation z to the n equals that particular number, then one of the solutions is here. Here's the rectangular and polar coordinates of this particular solution, but here's the whole set of all of them, and you can see them graphed. So really kind of a cool result that these roots have to actually have this really nice geometric property about them. And of course this works for natural number roots. And actually, the bigger you let this root be, the smaller you're making that circle's radius. And the fewer points, and the more points you have on it, but all equally spaced. Okay, that gives you some idea about powers and roots of complex numbers.